Welcome to the AI Research Roundup. I am your host, Alex. Today is May 12, 2025. We're diving into an ICLR conference paper, Faster Cascades via Speculative Decoding, published just over 3.5 months ago on January 22nd. This paper explores making large language models quicker and more cost-effective. It proposes combining model cascading, where a small model passes tough tasks to a larger one using a deferral rule, or decision point, with speculative decoding, where a small model drafts outputs or tokens for a larger model to quickly check. The goal is to get the best of both approaches. Alright, so this first figure shows their proposed speculative cascade. A small, autoregressive model, which generates tokens sequentially one after another, acts as a drafter. Its drafted token probabilities, called QT, go to a verifier. This verifier has the large model and a parallel deferral rule. The large model provides its own token probabilities, PT. The deferral rule then uses both QT and point to determine the target distribution, pi-t, effectively the system's final decision on the next token's probabilities. This parallel setup is crucial for the desired speedup. Building on that parallel setup, this table lays out various inference strategies. It details their deferral decision rules. These are the conditions determining when the larger model steps in. Their target distributions, which is essentially the system's final decision on the next token's likelihood, and whether execution is sequential or speculative. Notice how the proposed spec cascade methods, like spec cascade OPT, all use speculative execution. That OPT rule even incorporates the total variation distance, or DTV, a measure of difference between the small and large model outputs, to make smarter deferral choices. Okay, so this next table really highlights the performance gains. It compares different methods, showing latency reduction, essentially how much faster they are, when matching the large model's quality. It also shows the best quality achieved without being slower than the large model. Quality here is measured using scores like BLEU, which is the Bilingual Evaluation Understudy, a common metric for translation quality, and Rouge 2, or Recall-Oriented Understudy for gisting evaluation, often used for summarization. Notice the Spec Cascade OPT and Spec Cascade token methods, particularly with a small to XL model setup, delivering significant speedups, like up to 2.61 times faster on the WMT task, alongside top quality scores. Following those impressive speedups, these plots here further illustrate the quality versus rejection rate trade-offs. Across diverse tasks like translation on WMT, measured by Bilingual Evaluation Understudy, and coding on MBPP, we see performance when interleaving Gemma 2B and 27B models. The rejection rate on the x-axis indicates how often the larger model intervenes. Consistently, the spec cascade token method achieves higher quality scores for a given rejection rate. For instance, on MBPP, it gets a better pass at 1 score. That's a metric checking if the top generated code passes unit tests, clearly showing its superior efficiency. Alright, shifting to some of the underlying mechanics, this table details the acceptance criterion. Essentially the rule for deciding if a token drafted by the smaller model gets used for various speculative strategies. It considers both non-greedy decoding, where temperature is greater than 0, introducing some randomness, and greedy decoding, where temperature is 0, meaning the model always picks the most probable next token. The key insight here is that under these greedy conditions, their spec cascade using the token v3 deferral rule shares the exact same acceptance rule as a lossy speculative decoding approach, which is a version that might trade some quality for speed. This shows a neat theoretical alignment. So building on that alignment, these plots here give us a really clear visual of quality versus latency for different token-specific speculative cascade deferral rules when using T5 models. We're looking at tasks like WMT, XSUM, and CNNDM with quality on the y-axis, measured by Bilingual Evaluation Understudy, or Recall-Oriented Understudy for gisting evaluation, and relative latency on the x-axis. That dotted line represents the large model's quality. Notice how Spec Cascade Token v3, in green, consistently offers better quality for a given speed, often outperforming the lossy speculative decoding baseline and getting very close to that large model quality much more efficiently. Okay, so we've seen how these speculative cascade methods, especially with rules like token v3, really push the boundaries of efficiency. The big takeaway here is that by cleverly implementing cascade deferral rules through speculative execution, essentially having the larger model quickly check the smaller model's drafted outputs in parallel to make that deferral decision, these techniques successfully combine the best of both model cascading and speculative decoding. This ultimately means better quality for a given cost and much faster results from our LLMs. That's all for this AI Research Roundup. Thanks for tuning in.